Okay. So last time we started talking about like field strengths, right? Ligand field strengths. And we said that if we have an octahedral system, drawing big today for some reason. What was the orbital labels of the triply degenerate orbitals?
Was that the EG?
That's
or was
the
that
top one.
Oh, the 2TG then.
Yeah.
Or the T2G, yeah.
The way I remember it, T triple that way. Okay, and then we have our octahedral field splitting, delta O. And now we had strong field ligands and weak field ligands. And strong field ligands, what happens to delta O? Is delta O large or small?
Small.
Nope,
Large.
other way around. Not trying to confuse you this time for once. Large. And when it's a weak field, it's small. Okay. And last time we looked at like the halide ions, we considered pKa's of a couple different systems. So now what we're going to do is talk about a series, what's called the Spectrochemical Series. What you can do is you can make an octahedral complex and you change the ligands. What happens is the color changes. Because what's happening is these ligands are modifying this delta O and it's changing what's known as a D to D transition. Let's talk about the Spectrochemical Series. And what it is, it's a list of ligands that gauges delta O. Okay, so we're going to have strong field ligands on this end, and we're going to have weak ligands on the other. So we got CO, CN minus, which is less than phenyl, which is less than NO2 minus, less than EN, H3, NC, H2O, F minus, R2 minus. I'm going to run out of space. L minus, BR minus, I minus. Okay, you can look these up. So we said strong field. What do we know about delta O for strong field systems?
Very large.
Yep, it's large. Okay. Oh, I'm sorry, this is meant to be small. So weak field, they're small. Okay. If you had to guess what type of complex you would you make a high spin or a low spin complex with a large octahedral field splitting?
Low spin.
Yep. That leaves this guy as a high spin. Okay. Now let's talk about the pi acidity or the pi accepting nature of these ligands. Do the strong field ligands or do the weak field ligands, which ones behave as better pi acids or better pi acceptors?
Are the weak field ones?
So these guys, you're saying are better at
I
accepting?
think it's the CO. I think those halides are better pi donors and pi are sigma donors. I think,
Okay, so Josh says that these guys are better pi donors. These guys are better sigma, or I mean, pi acceptors. Tara, what do you think?
Yep, sounds good.
Are you just going with it just because?
Yep.
Not a good enough reason. Maddie, what do you
Yeah,
think?
good enough.
I think that the high spin would be acceptors.
Okay, you think these guys are acceptors. John, what do you think?
So yeah, I can't come up with like a logical reason to like choose either one.
Okay, so let's think about the nature. Let's go with the extremes. We got I minus, and we got CO. These are both sigma donor ligands, right? What about their pi ability? Do they want to accept electron density into their pi system, or do they want to donate through their pi system?
Iodine wants to donate.
Yep. And then CO, remember when we talked about back bonding?
Yep.
What happens with CO, like when it binds with a metal?
It's gonna get back bonded through its like technically anti-bonding p orbital.
Yeah, so through the
Pi orbital.
anti-bonding pi orbital, it accepts electron density from an occupied UA.
Isn't it the carbon accepts the pi electrons? That's
Well, it's more of the carbon monoxide as a whole accepts the pi, accepts electrons that way. So these guys, these high spin cases, or excuse me, low spin, large octahedral field splitting, these guys tend to be pi acceptors. Well, these for the weak field tend to be pi donors. If we think back to like those molecular orbital ligand field diagrams that we were drawing, I'm going to pull this in front for a second. We had this really complicated drawing. Here was our T2G orbital, here was our EG. And remember, with pi accepting ligands, what ended up happening is we caused a greater shift in this delta O, this T2G level, which was hybridizing with unoccupied pi star orbitals. This was getting lower in energy, right? Whereas if we have systems that are pi donating, what's actually happening is this T2G orbital is destabilizing and it's moving up in energy, making our octahedral field splitting get lower. So we have the spectrochemical series now, and we can look at the spectrochemical series. We can consider what type of metal we have, like how many electrons it's got. Look at this. Is a strong field, weak field, and decide if it's a high spin or low spin complex. So let's look at an example of this. Am I okay to move this paper away? Okay. So, example. Would you expect FeCN6 3- to be high spin or low spin? And the other thing we're going to ask is how many unpaired electrons? Okay. First thing we have to do, we have to determine what do we want to figure out?
If it's high spin or low spin.
Yeah, we want to determine if it's high
So
spin or low spin. What do we got to
determine
do
the type
before
of
that?
what type of ligand cyanide is?
Okay, let's consider that. So we got Cn minus. What type of ligand is that? Looking back at the spectrochemical series.
Strong field.
Yep, it's a strong field ligand. Geez, this thing focused. There we go.
On our test, are we going to be given that series chart, or is that just something we're going to have to know?
That's something you're going to have to know. What you really want to consider is it pi accepting or is it pi donating? That's like the biggest hint. So looking at strong fields, what does that mean for the octahedral field splitting?
It's large.
Large. Yep.
So low
Okay.
spin.
Well, we have to consider a couple things first.
Oh, all right.
Can we have to know the number of d electrons to determine if, like, did we even have to do this? We might just end up with a case where we have all high spin, all unpaired electrons, or we might end up with a case where it's impossible to end up with a high spin case. So we have to
When
consider,
like considered high spin or low spin, and like I would understand it for like the case where it's all about the d orbitals, but if it like, let's just talk about like the p, like just because you have just like 3 electrons in that, like if we took I think it would be like nitrogen, so is nitrogen automatically considered high spin?
nitrogen is considered paramagnetic because it's
Okay,
it's an atom that's by itself, so it's a bit different.
Okay, gotcha. So is it just compared to a different state, or is it just like you have to have a certain number of electrons in the like same spin?
You have to have a certain number of electrons, like you have to have, what is it, D5 to, what is it? I think it's maybe once you get to D8, you can have a high spin and a low spin case there, I think, too.
Okay.
So, well, let's consider that. So first thing is we have to figure out how many d electrons are we dealing with, and let's draw the crystal field diagram for this system. So we got iron. What's iron's oxidation state in this complex?
3. Wait, no, it's
Mm-hmm.
3+.
Yep. Remember, what's the charge on each cyanide?
-1.
Overall charge on the cyanides?
-6.
Yep. Now, whatever the iron is has to add to that -6 to get a -3 plus 3, right? Okay, so we got an iron 3. Let's check out the periodic table. So we got iron 3+. This is my mouse pad. I am that much of a nerd. It saves me a lot of time. Don't judge. Okay. So we're talking about here, what is the condensed configuration for iron 3+ going to be?
So it's gonna take the s electrons.
Yep, those are gone. And
so it just becomes, what is that, like 4? No, 3.
4p3, whatever it is. Then 4p3, was it like krypton or something?
so we got argon over here.
Yeah. Oh, argon. Then
Fe 3+,
and then 3p.
argon. The s orbitals are gone, so now we got our d orbitals. And remember, 2 s orbitals are gone, 1 d orbital is gone.
So d. So what's it? 3d3.
Yep.
No.
Well, not 3.
3d5.
3d5. Yeah.
Yep. 1, 2, 3, 4, 5, because we've removed one of these electrons. So we're at 3d5. So that means what type of metal do we have?
D5 metal.
Yep.
So that's what?
Okay. So now let's draw our octahedral fields splitting. What's it going to look like for octahedral systems?
It's going to be 3 on the bottom and 2 on top.
Yep. And we got 2 cases here, right? I'm going to draw both of them. Okay. Which one's the high spin? Which one's the low spin?
The high
The
spin
left
by
is
the
high.
left, right?
Left one is high spin, yep. Leaving the right one low spin. Okay, so we said we got a strong field ligand, delta O is large. Which of these two is more likely our electronic configuration or electronic structure? Are we going to have the high spin case or are we going to have the low spin case?
Low spin.
Yep. This is our complex. And how many unpaired electrons do we have?
1.
Yep.
Wait, how do you know it's not the high spin just by looking at this?
So you have 2 options, right?
Yeah.
High spin cases have more unpaired electrons, and if you add up their total amount of spin of those electrons, it's larger for the high spin case. Does that, because in this case you have a plus 1/2, plus 1/2, plus 1/2, plus 1/2, plus 1/2. In this case you have a plus 1/2, minus 1/2, plus 1/2, minus 1/2, plus 1/2. Does that make sense?
What if you had like a D9, then with a high
Okay.
spin?
So let's look at a D9.
Well, so the reason that we chose low spin here was because of the cyanide, right?
Yes, we
because
chose
that-
low spin because of the cyanide. But Tara, oh, I thought you were asking like how do we know or what were you asking? I'm sorry, Tara, I got
Oh,
confused.
never mind.
Okay, well let's consider a D9 metal though, real quick. So let's say it's in an octahedral field. Okay, let's start filling electrons. 1, 2, 3, 4. Can we have any other case?
Could have one excited.
Yeah, well, yeah, we could have something like up here. Yeah, sure.
Oh, I mean, like you could have an electron to transition to the top and.
Oh, okay. D9, we'll call it D9 star.
Sorry. And that could technically be your high spin, I guess.
Well, if you look, is there any difference between the total amount of spin?
No, there isn't actually. Okay.
Yep.
Just the energy
So-
difference.
This is a weird case. You wouldn't see that too often except in like excited states. So D9s only have one state. Same with like D10s or D0s.
So is that a high spin or a low spin?
Neither.
It's a medium
No
spin?
spin.
No, it's just is what it is. So let's see. Your book sometimes I think it considers that a low spin case. But technically, there's no difference in spins, so let's see. There's a nifty diagram. Where are you? We're getting closer. Maybe. Thought I had it. Give me a second, I'll find it. Maybe not. All right, fine. Wants to do it the hard way. Let's look up high spin. I can't find it right now.
Okay, I'll look it
But
up.
there is a good diagram. It's killing me. I can't remember where it's at. I feel like it should be close by in here, doesn't it? But what it does is it has like a diagram that shows you each of the possible different types of spin that you can have. Is that in this book or is it in another book? And in that, here it is. Geez, it took me forever to find it. So what it is it's showing the different cases. You got the high spin up top, the low spin in the bottom. And as you can see, the ones that are boxed are systems that can have a difference. So in this case, you wouldn't really call it high spin or low spin. You would just call it a D8 system. Does that make sense?
Yeah.
Yeah, that's what I was looking for. Geez, it took me a while. Okay.
I keep like my internet just keeps cutting out for some reason, so I kind of missed all that. But is D8 just like inherently high spin?
D8 is just a D8 metal. It's not considered high spin or low spin because if we do a D8, well, excuse me, if it's in an octahedral field, the type of ligand setup you have can make a big deal. So even though we said D9s are just called D9 metals, that's in an octahedral field. There might be other systems where that's not true. Like for example, I don't know, we could have, what is it, like a splitting?
Yeah, so like in tetrahedral might change a little bit.
So what type of, this is a good question. What type of ligand field splitting is that?
Square planar.
Labels.
Yep, that's what I see too. So let's say we had a D9 system, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's all we could get, right?
Right.
Okay. But if we look at a D8, we got two options. 1, 2, 3, 4, 5, 6, 7, 8. 3, 4, 5, 6. Like that, right? So one of these would technically be considered the high spin option. Does that make sense?
With the high spin being left.
Yep, the high spin's the one on the left. You have to consider what type of ligand field you have before you can actually say, is this a high spin or a low spin case? So first decide, is it octahedral? Is it square or planar? What type of geometry do you have? Okay. Let's look at one more example. What would you expect for CO, CL 6 2 minus? high spin or low spin complex? Okay, first thing we want to ask, what type of geometry do we have?
Octahedral.
Yep. Got octahedral. Okay, let's look at what type of metal do we have? So
Well,
how,
cobalt is 4+. And
is
so,
it 4 plus?
Yes.
yeah.
Okay.
I was like, wait, what?
Is it two and three?
Oh, it's a be D.
So D4.
Yep, it's a D4 metal. Everybody clear on how to get that? Is it D4?
Yes. Because you took
Because
away
of 2S.
2S and 2D.
Mm-hmm. Let's write out the
It's not gonna
complete.
steal anything because it doesn't help it.
Let's write out the configuration for cobalt. So,
I mean, unless it does steal it, because like
So it'd be AR,
yeah, AR.
3D.
Well, let's do, we're writing the
Wait,
full
okay.
thing for cobalt right now.
Or it might not be.
S square.
4s2, 3D. Let's
Three,
Was
count.
it a 7? No.
7.
1, 2, 3, 4, 5, 6, 7.
Oh,
Yep.
7, then that makes it a D5.
Yep. Okay, so now we're at cobalt 4 plus. Argon 3D what?
3D5.
Yep. So we got a D5 metal. Okay, same sort of thing. We could have a high spin or a low spin complex, right?
how are we supposed to know, like, if it's gonna steal the electrons from the 4s orbital? Like, do we just have to know the cases, or
Oh, like is that chlorine gonna steal electrons?
no?
or-
For the cobalt,
Mhm.
how do we know if it's gonna steal the 4s2 electrons to the 3D?
Oh, like how do we know? Well, remember
It's all
when
about-
transition metals get ionized, the 4s is lost first because radially it's further out and it experiences less shielding. So that's one of the easier ones it is to pull off
Gotcha.
for that reason. Okay. So we got a high spin case, we got a low spin case, right? Again?
Yep.
Let's look at the ligand. Weak field or strong field?
Weak.
Yep. It's weak. Okay, so if we have a weak field ligand, what does that mean?
You have a small delta O.
Yep.
I spin.
So you have
What'd you say, Maddie?
I spin.
Nope, remember, weak fields. Oh yeah, you're right.
Yeah.
Yeah, I was gonna say, she's
Yeah.
right. It's high spin.
Sorry,
May
I got
5th,
confused.
10:36.
Even I get confused. High spin. There we go. So this is what we got. We got a high spin complex. Everybody feel comfortable with those steps? Okay. So one more thing I want to point out is that other fields, like we said, depending on if you have like square planar, trigonal, bipyramidal, and so on, you have different splittings. So other geos have different field splittings. Ligand field splitting energies. So we draw these little dashes and stuff, and we haven't really indicated how far apart in energy these orbitals are from one another. So I'm going to move this up. Generally, as an example to illustrate this, we're going to have two different types of complexes, and then we're going to talk about their field splitting. We got tetrahedral, and we got square planar. So in octahedral, we put the field splitting was delta O. What do you think we're going to do for tetrahedral?
T.
T.
Yep, delta T.
And square
That's a-
planar is SP, I'm assuming.
Yep. Delta SP, and that's approximately 1.74 delta O. So looking at the scale, if we were considering tetrahedral, tetrahedrals actually generally have a smaller octahedral, or excuse me, a smaller field splitting or ligand field splitting. And its scale is about 4/9 of the octahedral field splitting. Square planar, it's the opposite. It tends to be way larger. So just keep that in mind. Most of the time with those square planar complexes, even though we drew this, like this D8 one that had a high field or had a high spin, most of the time D8s or square planar systems will not have a high spin, just because this energetics is so much larger than what we're considering for like octahedral and for tetrahedral. Okay? Any questions about that? No? Okay, we're going to talk about the Jahn-Teller effect, and then we're going to talk about colors afterwards. Jahn-Teller effect. So you guys already know a little bit about the Jahn-Teller effect back when we were talking about solids. We were discussing H2 and what would happen to it. We called it a Peierls distortion too. Can anybody describe to me what the Jahn-Teller effect is?
It's all about like having your two different like kinds of I can't remember. I just remember it like makes a larger gap in between them.
Mm-hmm. It makes a
What's it,
band
like the
gap in
band?
solids.
Yeah,
Yep.
which is like
What-
representing. Yeah.
What happened to make that band gap happen? You remember what we allowed the hydrogen atoms to do?
Didn't they like break apart until they're?
Yeah, what were you saying, Josh?
Wasn't it like they were breaking apart or decomposing until they? No,
Yeah.
that's not right.
Instead of just being a linear chain where the hydrogens were all equally spaced, they broke apart, and
To H2.
some of the hydrogen distances shrank and some of them elongated. So like these ones would elongate, these ones would shrink. And we made H2 units. So basically what's happening in a Jahn-Teller distortion is the geometry is changing. Bonds are being constrained to force the system from that was once paramagnetic to become diamagnetic. So a geometric distortion that occurs when degenerate orbitals are unequally occupied. So let's consider a D7 octahedral complex. And what we're going to do right now, we're not going to consider the ligand field. We're actually going to consider like what do those MOs look like for this system. Oh, I didn't want to draw that one yet. All right, I'm going to go to a new page. Draw that one. Okay. I screwed it up again. All right.
All right.
Third time's the charm, right?
Three.
There we go. We did it. Yay. Okay. Orbital labels for this bottom one.
T2G,
Yep. Top one.
EG.
Yep. Okay. And in this one, we have a completely octahedral complex where all the bonds are the same length. Okay, now let's say we were to extend the axial bonds. We were to make these guys get longer. So we got metal, and we're going to show which ones got longer with dots. Like that. What's going to happen to this ligand field?
If those ligands extend, then would it remain in low spin still, or no?
Well,
Well,
yeah,
would they even be considered connected in that case? Are they still technically?
we'll say they're connected. They've been spread far
To the
away.
extent.
So, is anything going to happen to these T2G ligands? What D character do these guys have again? These ones up top or what? They're D.
Z squared and
D is E squared and D what?
DX.
DX squared, yeah.
Y
Yeah.
squared.
And then these other guys are the rest, right? There's D, X, Y, D, X, Z. Which one am I forgetting? It ever focuses.
The D,
Y, Z.
X, the,
Yep,
yeah,
Y, Z, yep. Okay, so now we're elongating along here. What is anything going to happen to these other energies, really? Like these guys, are they going to change?
Probably not.
No, they don't really get influenced a ton. These ones are going to remain. What about these orbitals?
It'll be higher in energy.
Which one's going to get higher in energy?
EX squared.
Would it be DZ squared?
Yeah.
Go up.
Yep, these guys are going to get higher in energy, right? Because what's going to happen, these ligands move away, these bonds are going to shrink a little bit. So XZ is going to move up a little bit higher in energy. I mean, dx squared minus y squared is moving up higher. What happens to the dz orbital?
Same.
It's going to get higher in energy with these ligands moving away from it.
It's going to get lower in energy, you said, because
Yep.
it's going to get closer to the metal center.
Right. So the dz squared is going to get lower in energy because these ligands move further away from that orbital, stabilizing it more. Now if we look, we get a situation where the system is a little more favorable. It ends up breaking that degeneracy. Now let's consider the other situation. Let's say we make the equatorial bonds larger. Extend equatorial bonds. So in that case, we're moving these guys out. Okay, these T2G orbitals are not going to be influenced a ton. But what's going to happen to the dz squared and dx squared minus y squared?
That's going to shrink in, and the z is going to push out, so the opposite of what we just observed.
Yep, dz is going to move higher in energy. Why is the dz going higher in energy?
It's farther away from the metal center.
When you say it, what do you mean?
Never mind.
So we're talking about these ligands, right? Are they getting closer or further away to these orbitals? When they get closer, the energy shoots up.
Farther away. So yeah, it should go down.
Yep. So if they're getting further away, it's stabilizing that orbital more because you have these negatively charged ligands that are moving in, really unfavorable to do that. Okay, so now let's look at an example of this. We're going to say, would you accept or predict bond lengths we're going to look at? So would you expect the same bond lengths for an NCU bond, an NO bond, in this complex? Okay, first let's do a little bit of review for your exam. Let's try and name this thing.
Oh shit, I forgot about that.
Okay, so
He's like, oh god.
let's get the naming. What comes first?
Let's
Copper is
go.
last.
How we just
So
start?
it's going to be aqua, so it's going to be biz.
Remember, aqua or amine? Which one comes first?
Oh, I know amine. Yeah, you're
Oh
right.
yeah, oh that darn alphabet.
Tetra amine with two M's.
diaqua copper.
Copper, and then,
2 plus.
okay, so you want to do it this way.
Yes, sir.
Okay, now what about, there's another way we can do that with the, not the EB naming convention. Diaqua copper.
Shouldn't there be 2 A's as well? Shouldn't it be tetraamine?
There should be 2 A's.
Ooh, points off, Dr.
Oh, there we go.
Simpson.
Minus points.
off.
Minus points.
Bonus points
You
for
points.
us.
Minus
Yeah.
30.
Plus 1 on my test. That's
Man,
okay.
I'm
That's
getting a D in this class
It's
now.
minus
Yeah.
1 for every time you ask for extra credit, Josh. Read the syllabus.
So,
End of the semester, everyone's coming after
yeah, man, everyone's vicious. What would the Roman numeral be?
her.
It would be 2 minus? No.
Two
No, it's
minus
just a-
Roman
It's not even
numeral.
possible. Yeah, that would wait a second.
Worst.
2.
Oh wait, no,
Yep,
just
it's
be
still
2.
2.
Yeah, it's just 2 because none of them have charge.
I was
Yep,
thinking
these
amine
ligands
had a
don't have
plus.
charge. Okay. So now, what do you suggest we do next?
Take a 5-minute break after using all those brain cells.
And after we get done with our break,
I guess come up with the geometry and just start going through it.
okay, so geometry, what type of geometry are we going to have here?
Octahedral.
Yep. We got an octahedral geometry. What next? Well, let's draw it. I'm realizing now there are 2 ways. We should have done one other thing. Should have said trans. There we go.
Oh yeah, because technically.
Okay.
We're going trans.
There's no way this is going to be 100% right on the test.
Yeah, you're gonna be handed like partial credit left and right here.
I'm
We're
gonna
gonna be
miss
missing
something.
something. The second you add that clockwise or counterclockwise,
I'm
it's
put
going
rubber
downhill.
for
I
no
am
reason.
giving up. I am turning it in.
Just give it up. We've come too far. I can't give up yet.
That's what you think.
Yeah, you're overestimating to get through this.
How come you always use octahedral? I feel like on the exam you're not going to be using octahedrals.
Octahedral is just the easiest one to go with.
Imagine.
So yeah, you're not gonna give us this on the test. Yeah.
I might give you a tetrahedral. I might ask you about like the ligand field diagram of the other ones, but when it comes to explaining things, I'll typically stick with octahedral and tetrahedral.
I was gonna say our daily problem had 5 different geometries, and I was like, if that's on the test and we have to know this splitting, then I don't know.
Yeah.
Nope, that's grad level stuff. I won't be that mean to you.
I can get close, but it's never going to be right.
Right. And the other thing is octahedral tend to behave a bit better than the other systems. So you can predict those ones a bit easier. Okay. So now, what do you want to do next?
We could draw the.
So, yeah, probably come up with what its crystal field thing is.
Okay. How many electrons do I need to draw?
Copper's a 2 plus.
So Cu2 plus. What type of metal is that?
Be D9.
D8. No, not
I
D8.
need a periodic
Is it?
table.
No, I think it's D9.
Okay. Here's a periodic table.
It's a D7. No, D9. D9. Yeah.
D7.
But it's +2, so.
Yeah, D9. So,
Oh,
'cause it
totally
takes
over
away
there.
from the-
For some reason, I was
Yeah.
looking at CO. I was like, wait.
Yep. D9. Arrow is right at the beginning.
Wait, but isn't it 2 plus? You
Sarah's
said-
always right.
Yeah,
Yeah,
so the
but it's
s
gonna
orbitals.
remove
Or s orbitals.
S electrons.
Those
first.
s orbitals always go away
Be
first.
confident, Tara. Be confident.
Okay, so now let's write this out. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Now this is an idealized world where all the ligands are the same, they're point charges. Do we have that here?
Are these ideal
No,
point
because
charges?
they're
I'm
not
gonna
all
say
the
no.
same ligand.
Yeah, they're all not the same ligand, so the splitting is going to change a little bit, right?
Mhm.
Right.
Okay. So looking at this complex, which one do you think is going to have longer bonds? Which one do you think is going to have shorter bonds?
I think the O is gonna have a shorter bond.
I think the O is going to have a shorter bond.
I'm gonna say it's gonna have a larger
More
bond.
It's
electronegative.
more electronegative than nitrogen, so it's gonna hold them closer.
But there's more nitrogen.
Now we got to that is
But
reasonable logic.
Yeah.
But
it's
what you
okay
want to
with
do,
the
you want to think
but.
about the spectrochemical series.
So because the NH3 is a stronger field.
Oh,
Yep. So that means it's going to have a stronger impact on the bonding, right? So the bond distances are going to be different. So looking at that, what's going to happen to this system?
So the NH3 bonds are going to bond closer, and the OH, the waters are going to extend out, so their axial positions are sticking out. And as a result, you get the D x squared y squared, the higher energy, and the DZ squared is a lower energy.
Exactly.
attaboy, Joshua.
There's a couple points on the test.
Yep, pretty much. So that's exactly what happens. Since these are different ligands, the axial ones bond less strongly, so the DZ squared gets a little more stabilized. So the answer to this then would be no. Due to a Jahn-Teller distortion, should be a capital T. The NC distances are shorter.
Would you
And,
be able to go way back up for just a second after you're done writing that?
Yep.
Just to like what the question was. I think I wrote that down wrong.
Yeah, sure. It said, the question was just asking, would you expect the same bond lengths for nitrogen copper bond? Oops,
Yeah.
I wrote it down wrong.
Okay, so I like was reading what the question was. I was like, what in the world did I just write?
Yeah.
CuO
I'm guessing
bond,
that's
there
O
we
to
go.
Cu. Yeah, okay.
Mhm.
I was like, I didn't realize that nitrogen was bonded to oxygen in this case.
No, there are no nitrogen oxygen bonds here. So if all these ligands were behaving exactly the same, this Jahn-Teller distortion wouldn't happen. And in some cases, you can actually make a system that was once paramagnetic become diamagnetic. Just like we talked about butadiene way earlier on in the semester. Okay. All right, let's talk about one more thing and we'll be done for the day. Everyone looks extremely drained.
Thinking about that test and how we got to study for it, and then we have that presentation later today.
Yeah, woo!
Yay.
That'll be good. We're going to talk about chapter 11 really quick. Coordination chemistry number, what is it? 3. Electronic spectra. So the sad thing that you guys didn't get to experience this semester is that when you make these transition metal complexes, they're extremely colorful. Like they're deep purples, deep blues, greens, really pretty colors. So many transition.
I say this is way cooler than organic lab.
Oh yeah, it is. You'll learn a lot of cool techniques in it too. So what does that tell you about the type of electromagnetic radiation that they can absorb?
They absorb visible, I'm assuming.
They absorb visible light. So let's refresh everybody's memory. Let's talk about the absorption of light.
Wait, is it that they absorb or technically reflect? Because if we're seeing it,
They absorb. There is like Rayleigh scattering, like why the sky looks blue. That's a bit different. Where the size of the system deflects that wavelength and it scatters the light.
I know what you're saying, John. You're saying that like the light,
yes,
the
it's
color
technically if
we
it's
see is
absorbing
the light that
we're
the wavelength that
seeing.
they like reflect or that they don't absorb.
Right. Yeah. We see what they don't absorb essentially.
Mhm.
So, question: if a solution is green, what colors is it absorbing?
Orange.
Oh my goodness. Let me look up my
Oh, it's red.
Yep, red. Red. And do you remember what type of color that is? Compare it like red and green, or what type of colors to one another? You remember?
art class now.
Secondary to primary, is that?
No, it's complementary or not complementary.
Yeah, I just made that up. Totally.
Secondary is a word though. We had to learn.
Thank you, Miss Missile.
Yeah, I remember. Yeah, exactly. I remember being in like middle school and like trying to learn
Yo,
about
art
this.
used to be my thing. Making
It was
like
like
those
color
clay.
theory. It was so dumb.
Yep, it's a color wheel. Okay, so we got red, green.
Will this be on the test?
Yes.
You will need to know this to
Jesus
answer some of the
Christ.
questions.
It's helpful for dressing.
Something, yeah.
Some of us are colorblind, Maddie.
Oh,
Tough.
I'm wearing actually a navy blue fit right now, so it doesn't affect me.
Better than me. When I wear all one color, I feel bad. I'm always
I
blue.
always do.
Both gray. You can't.
Right, you can't go wrong with gray.
No.
So what's blue's complementary color?
Yellow, orange.
It's
Yep.
orange, yeah.
Maddie, how do you know these?
Because we literally got tested on this every day in middle school.
And then blue and
Yeah.
red makes purple.
Yep.
Ooh.
Actually, violet.
Senior year.
It's violet.
We go from advanced quantum mechanics to talking about purple. Yay!
The
Yeah.
one time I excel in this class.
Okay.
Strong.
So know that, remember that. We're gonna need it in a minute.
Maddie's gonna get that question right.
Well, yeah,
Pardon?
that's what I got my doctorate in, you know.
I'm gonna have to write this down on my hand for the test. I don't know.
I could even tell you which ones are the warm colors and the cool colors.
Oh my god.
Well, that's an easy one.
This is
Yeah,
warm and cool
primary and
colors.
secondary.
So in most transition metal complexes, definitely octahedral ones, the color is due to something called a D to D transition. It's known as a forbidden transition.
Stop. That's not real.
No, yeah. They just started calling them transition or forbidden transitions because they violated certain rules, but they still happen. And the lingo stuck. Okay. So again, we've drawn this octahedral field splitting a million times. That's delta O. What's the top label?
EG,
Yep, bottom.
2TG.
Okay. And what are we talking about here? Like, what does that delta O mean?
The change in energy of the orbitals, or the difference in energy of the octahedral orbitals.
So delta O corresponds to delta E, a change in energy, right?
What is it called? The forbidden?
Yeah, they're called forbidden transitions.
Like a lot.
They make it sound much cooler than it actually is. So since these correspond to an energy, that means they also correspond to a certain wavelength, right? So if we change this octahedral field splitting, we'll change the wavelength that these systems will absorb. And that's where the spectrochemical series comes in play. The way that they identified this is they made these octahedral field complexes, and visually they could see that the color changed. They didn't have much in terms of instrumentation to actually measure this at the time, but they could look and see, hey, something's happening here where the electronic states are getting perturbed. And what's happening is that delta O is changing in terms of its energetics. So let's talk about redshifts and blueshifts to describe what's happening to that delta O. Redshifts and blueshifts and delta O. So when we're talking about a redshift, like if you think back to physics,
Farther away. Or
The
it's
way,
slowing
like-
down. I mean, depends on what you want to talk
Yep,
about.
so-
Example.
so a redshift, I don't know, let's say the ambulance is driving towards you. What happens to the pitch or the frequency as it drives closer to you?
It's higher.
Increase.
It's higher.
Higher. Now, what about as it drives away?
It's lower.
Lower. Which one's the red shift and which one's the blue shift? Is the red shift when the ambulance is driving towards you?
Isn't it when it's driving towards you because it's like getting more intense? Isn't that like red and
Other way
blue is
around.
like it's cooling down?
Other way around.
All right.
So it's actually shifting to. Oh wait. No, you were. Let's see.
No, because red shifts when a star is like going farther away from you, that it shifts red.
Yes. Yeah, the red shift is when the star is.
I'm just going to stop answering questions about colors. Clearly, that is not my area of expertise.
Oh my God, Maddie.
Yeah, it's whatever.
Like,
They taught us the weirdest shit in middle school. I still have to.
That's all they're gonna get out of you. Everyone just smells bad and wants to break things. That's all that happens in middle school.
It was like that, and like our Christmas pageants in the church were like an army commanded thing. Very smooth.
oh my God.
But when Bree needed help with her religion homework, who helped her, Tara? Me. I knew it.
All right. So, what happens to the wavelength in a redshift? Are we shifting to a longer wavelength or shorter wavelength?
Order.
If we're shifting to a higher wavelength. And in a blue shift, we're shift to a lower wavelength. Oh wait, did I wrote it twice? You were right, Maddie.
Wait, so
Yeah,
it's redshift shifts to a higher frequency, lower wavelength?
No, it should be higher wavelength, right?
Yeah, because if it's higher wavelength, then it's a
Yeah.
lower frequency.
Because think
Well,
about
because
just like
red is
your
already-
electric, like your color spectrum.
Red
Like
is a
technically,
high
red has a
frequency, low-
higher wavelength, correct?
Yep, you're,
Yeah.
wait, no, yeah, yes, you are correct. Red has a higher wavelength, there we go.
Like,
But-
Blue shift, we're going to lower
frequency.
wavelength.
Yeah, but higher frequency too.
Yes, that's the next question I was gonna ask, so lower freak. Higher frequency. Okay, what about energies? Redshift, lower or higher in energy?
Lower in energy.
Yep. Okay, blue shift?
Higher in energy.
Yes, higher in energy. Okay. So now, let's ask the question. Oh, did you have a question? Oh, I pulled it away, that's why. So now that we got that straight, sorry guys. What happens to the crystal field or the ligand field as we undergo a redshift? What happens to that splitting when a redshift occurs? Okay, so we're going to assume we have an octahedral complex again. We undergo a redshift. Whoa. What's going to happen there?
the energy is lowering, so they're gonna get closer together.
Yep, the energy is lowering, so they get closer together. e.g. T2G. And in this case, if we're comparing delta O and delta O prime, which one is larger?
Delta.
Delta. Oh.
Yep. Okay, blue shifts, the opposite happens. Delta O is less than delta O prime. Okay, so now let's ask the question. FeH2O 6,3 plus is converted, converted to FeCl6 3 minus. Would the system experience a red or blue shift? And what we're going to do, will that work? We'll say assume low spin complex. And we'll be done, even though we're going a bit over. Okay. So we got an octahedral field. What type of metal do we have?
Probably just D8, just cause.
1, 2, 3,
5, I mean.
If it's a iron 3+, then
4. Nope. 1, 2, 3, 4, 5, 6.
iron 3+ is a D5 metal.
D6. Final answer.
Here's D.
D5.
It's just D. I just like with
1,
iron, I feel like
2,
it's
3,
D5 just
4,
every
5,
time. So
6. Minus 1.
I was gonna say we did it earlier in class.
yeah,
Yeah, we've done it a million times, right? So we got a D5 metal. We're pretending we have a low spin complex.
roasting tar right now.
Okay.
Okay, now we have H2O. Is that a weak field or a strong field ligand?
Weak.
Okay, so what does that mean about delta O?
That means it's small delta O.
Okay, then we're moving to a system where we got Cl minus. Is that a weak field or a strong field?
Isn't that weaker?
Mhm. So what does that mean? Delta O prime,
Even
It's smaller.
yep, is also small. But in that case, delta O prime is going to get smaller, right? Delta
Yeah.
O is greater than delta O prime.
So therefore it's a redshift.
Mm-hmm.
So we're meeting at 4:30. 4.
30.
I thought we were meeting at 4.
Oh, I wasn't trying to change the time. I just didn't know.
Oh, yep. Any questions about this?